Hello, everybody. My name is Jakob Snauwaert, and I'm a research and teaching assistant at the University of Ghent. Today, I will be presenting my research together with Professor Vanhoucke with the title, A New Solution Procedure for Multi-Skilled Resources in Resource-Constrained Project Scheduling. The main focus of this research lies on workforce analysis, and therefore I will solve the multi-skilled resource-constrained project scheduling problem, or MSRCPSP, for multiple different workforces. For this, I developed a problem-specific genetic algorithm that I will explain later on in this presentation. The desired outcome of this all is to analyze what the optimal workforce is for each given project and to find the ideal workforce project combinations. The goal is to identify what the ideal workforce size and characteristics are to match or fit with the project network and the requirements at hand. The outline of this presentation is as follows. I will define the extension of the MSRCPSP that our research focuses on, followed by my solution approach. Next, I will reveal some managerial insights, and lastly, I will set out future research perspectives. A quick summary of the MSRCPSP is shown on this slide. The decisions to be made are the scheduling of the activities and assignment of multi-skilled resources. The activities have a standard duration and require resources that master certain skills. Resources can only work on an activity if they possess one of the required skills of the activity, and a resource can only fulfill one of the skill requirements per activity. The skill availability of a skill type is the amount of resources that master that particular skill type. Most common objective for the MSRCPSP is to minimize the project duration or make span. In this research, the MSRCPSP is extended with two new resource characteristics, namely the breadth and the depth. Each resource has a breadth, which is the number of skills he or she masters. It can also be seen as the flexibility of the resource. A resource with a breadth equal to 1 is called a single-skilled resource. Multi-skilled resources, on the other hand, master multiple skills. The depth represents the efficiency level at which the resource can perform each of his mastered skills. The default level for depth is equal to 1. A depth higher than 1 means that the worker is more efficient and can finish an activity faster. A depth lower than 1 means that the resource is less efficient with his added skill. Due to the addition of the efficiency levels in the form of the depth characteristic, the activity durations are now variable. More particularly, the duration of the activity is now based on the depth of the assigned resources to each activity. In general, this is quite obvious. If you assign more efficient resources to an activity, the activity will be finished faster than if you would assign less efficient resources. To determine this new activity processing time that is adjusted to the depth of the assigned resources, we propose a reciprocal relation between the adjusted processing time of the activity and the average depth of the assigned resources. So, as you can see in this formulation, the adjusted processing time is equal to the standard processing time divided by the average assigned depth. But for this average assigned depth, we take it from the lowest skill type. So to clarify, this means that the adjusted processing time is only affected by the depth of the skill type with the lowest average depth. Therefore, resources that perform the same skill can influence each other. So a high depth can compensate for a low depth. However, resources that perform a different skill in the same activity have no impact on each other. So there is an influence within the skills, but not between the skills. We solved the MSRCPSP with breadth and depth with a genetic algorithm. This slide displays a schematic overview of our first basic approach. Afterwards, I will present how we extended and improved the solution approach. We first generate an initial set of solutions and determine their fitness value. Then we implement a two-tournament selection to select parent solutions from this population to generate new solutions and go through the search phase in a methodical way. The new solutions are then created using a one-point crossover and a problem-specific low-demand range crossover, which searches for and splits up ranges of activities that have a lower than average skill demand for a certain skill. Two mutators are incorporated in the algorithm, namely a swap and a modify mutator. Then we use a parallel schedule generation scheme to generate feasible schedules and resource assignments. And lastly, we implement two local searches, one of which focuses on the resource assignment, while the other focuses on the activity scheduling. In this genetic algorithm, the solutions are represented utilizing utilizing a chromosome of 2 n values, where n is the number of activities. The first n values consist of the activity list, which is of course the precedence feasible scheduling priority of the activities. The latter n values of the solution represent the new priority rule list, in which each activity is appointed a priority rule that determines the resource assignment. So as you can see here in the small example, we have two solutions. The only difference being in these two solutions that activity 1 uses resource priority rule 1, and solution 2, activity 1 uses resource priority rule 2. To the right of that, the priority rules are explained. So priority rule 1 prioritizes resource 1, and then the others, priority rule 2 prioritize resource 2, then 3, and then 1. To the right of that, there are some workforce characteristics. Resource 1 is single skilled and masters skill 1 pretty efficiently. The other two resources are multi-skilled and master 2 skills each. On the bottom left, you can see the requirements of the only activity in the small example. The activity requires 1 resource of resource 1, of skill 1, and 1 resource of skill 2. To the right of that, you can see the different assignments for the two solutions. Solution 1 first assigns resource 1 to skill 1, and then resource 2 to skill 2. The second solution first assigns resource 2, because that one is more prioritized, to skill 2, and then resource 3 to skill 1. For this priority rule list, we created a set of priority rules to determine the resource assignment. These lists are based on the breadth of the resources, the depth of the resources, and also the resource criticality, which determines the importance of a resource that is part of the workforce based on how many skills they master and how efficient they are. So if a resource masters more skills and they master them more efficiently, they have a higher resource criticality. By using this set of priority rules, we exclude a large part of the search space. However, by taking a diverse set of priority rules, we believe that we are still looking in the most promising part of the search space. So this is our first basic approach to solve the MSRCPSP, but there were still two questions: that the new representation perform at a satisfactory level, and is the set of priority rules good enough to have near optimal results? So therefore, I created another genetic algorithm that uses a representation for the resource assignments that was available in the literature, more specifically a resource list. So the solution was now represented by n plus r values, where n is again the number of activities and r is the number of resources. To clarify, the resource list determines the assignment priority of the multi-skilled resources in a single list. So as you can see here again from this example, the resource list only has r values, and in this case, resource 1 is most prioritized, and it's the same for all activities. Next, we solved each instance with this new genetic algorithm with the resource lists as a pre-processing step of our extended algorithm. So the resource list that then corresponded to the best found objective values were afterwards added to that initial set of 9 priority rules that I explained before. In the following figure, I will now compare the two representations, and then we can see some clear advantages and disadvantages that can be resolved by using the extended method that pre-processes the resource list first. So in case of the priority rule list, the algorithm can assign different lists to each activity. However, the priority lists are not optimized to the specific instance. In case of the resource list, it is optimized through the genetic algorithm. However, the priority order remains the same across all activities, which is not satisfactory in my mind. Using our combined approach, we can now include a different priority order per activity that includes the instance-specific resource list. And on top of that, the solution with the resource list is already an upper bound and can be added to the initial population of our first genetic algorithm. A comparison study showed that on average, the priority rule list with the basic set yielded on average a make span of 3.8% lower than a resource list, and the extended set of lists lowered it even more to 5.7%. I will finish this presentation with some managerial insights. First of all, the study revealed that for parallel projects, the workforce should consist of very flexible workers, meaning workers that master a lot of skills. This is because the more flexible workers there are, the more skills will be available and the more activities will be able to be scheduled in parallel. Secondly, for serial projects, more efficient workers are more important. This is because in this case, the resource assignment has the biggest impact on the eventual project duration. So we need to try and minimize each individual activity duration by assigning the most efficient resources, and therefore we can minimize the total project duration. Um, Lastly, in this table here, I have set out values for 5 different workforces for a single project. These workforces are made through several parameters that decide on the size and the characteristics of the workforce. And I also used some particular cost parameters. The first workforce in this table is a very big workforce with a lot of skills. And that's why it can finish the project the quickest, but it's also the most expensive. The second workforce, on the other hand, has a lower cost, which means it actually fits this particular project better, is however slower than the first workforce. The third workforce is the cheapest, but quite a bit slower than the previous two. Lastly, workforces 4 and 5 are dominated by the third workforce. What this means is that they are slower and more expensive. Important to say here is that while all workforces are vastly different, there is no best workforce here. Workforce 1, 2, and 3 can all be used depending on a certain deadline or budget, and even workforce 4 or 5 could be ideal if the cost parameters that I used were different. Now, in the next 3 slides, I will present some more managerial insights by answering 3 research questions that deal with the workforce characteristics. The first research question is how many mastered skills should there be in a workforce? For this, we disregard the resources for just a second and we analyze only the mastered skills. What we found was that the number of mastered skills should always be less than or equal to 40% of the total skill requirement, because a higher amount of master skills does not lead to an additional make spend decrease, while having extra skills available would definitely increase the cost. The results show that for parallel projects, the amount of skills should be lower than 40%, as can be seen in this graph. Higher skills lead to no make spend improvement. All values lower than 40% can be ideal, dependent on the cost parameters. For serial projects, this number is even lower, to 20%. It is lower for serial graphs because in that case, there are less parallel assignment possibilities which could benefit the extra skills. The second research question is how big should the workforce be in number of resources? The results show that the number of resources in the workforce had a lower impact on the make spend than the number of skills in the workforce. Moreover, for parallel projects, the make spend is higher for lower numbers of resources due to the skill constraints and the fact that the skills of multi-skilled resources cannot be utilized at the same time. The number of resources should also not be higher than 60% of the number of skills. A higher percentage will again not lead to make spend improvements. From the graph on the bottom right, we can see that for serial projects, the number of resources has little to no impact on the make spend. The make spend is in this case only affected by the number of skills, and how they are divided over the resources has no substantial impact. So the workforce can be both single-skilled and multi-skilled, it will have no impact. The last interesting research question that we want to answer is how many resources need to be multi-skilled in the workforce. The results revealed that the higher the percentage of multi-skilled workers, the higher the make spend, which seems counterintuitive because more multi-skilled workers means more skills, which should decrease the make spend. However, the make spend increases because we need to compare the single-skilled and multi-skilled workforces for an equal amount of available skills, in which case the single-skilled workforce benefits from not having to deal with the multi-skilled constraints, and the single-skilled workforce will in that case have more resources than their multi-skilled version. Hence, we try to analyze how much extra skills a multi-skilled workforce needs to compete with a single-skilled workforce in terms of make spend. The results showed that on average, a workforce with only multi-skilled resources needs to increase their skill availability with 18% of the total requirement to yield equivalent objective values to their single-skilled counterpart. This means that 18% extra skills are required to deal with the fact that multi-skilled resources can only perform one of their skills at the same time. For parallel projects, this number can go up to 50%, and for serial projects, it converges to 0%. These results can help managers to decide whether multi-skilled resources are more beneficial than single-skilled workers, because they can assess how many extra skills need to be trained and how many single-skilled resources can be fired at the same time. Lastly, some future research perspectives are to further investigate and analyze the costs of the breadth and depth of resources, and research how the cost of training a new skill compares to the cost of hiring an extra worker and how this further impacts the project. Furthermore, it will be interesting to investigate other kinds of impact that the depth of a resource can have on the project, such as cost differences, skill level restricted tasks, quality differences, assignment effectivity, or commodity usage differences. Okay, so this concludes my presentation. Thank you for listening. Right now, I will gladly answer any further questions.